Example 1.2. The charges and coordinates of these three charges are held fixed, where the charges are Q1, 2, and 3, -4, 5, -5 coulombs, respectively. Each square side is 1 meter and set K equal to 1 Newton meter squared per coulomb squared. Calculate the net force on Q1. The net force on Q1 due to charges Q2 and Q3 is given by superposition. In other words, F net on Q1 has to be the vector sum of 2 on 1 plus 3 on 1. The product of the charges determines the type of force. So in this situation, here's what we have. We see that the force of 2 on 1 is proportional to Q1, Q2. So if I multiply out these charges, I'm going to get -4 times 5. So this is -20, which is negative. That means it's an attractive force. Then I have force 3-1. So if I now look at these, this gives me +20, which implies that it's a repulsive force. To calculate the electric force, one must focus on getting the displacement vector. So let's look at the displacement vector. So picture-wise, I'm going to say that this is the origin. Okay, so here's my origin. So if I look at the force of 2 acting, remember, this charge is -4 coulombs. This is this is -5 coulombs, and this is +5 coulombs. Immediately, we see that there's a force that's acted upon from a distance of 2 acting on 1, and it's going to pull it in this direction. So that has to be the force of 2 acting on 1 along a straight line. So now if I look at the second force over here, it's going to apply a force along a straight line, and it's pushing it away into the third quadrant. So when I look at my displacement, I have to have a vector that's in the positive direction for 2 to 1, and I have to have a vector in the third quadrant when I have 3-1 acting on this. So in other words, we see here that the unit vector R21, that this guy has to be in the positive I direction. On the other hand, the unit vector 3, 1, that has to have a component both in the negative x and negative y direction. So now let's go calculate these quantities here. So I want to start with displacement. Vector R21. So the displacement are, we have R1, which is going to be -20 meters. And that's because it's 2 squares to the left. And then I'm going to have R2, which is 2 squares to the right. And so I know I need a vector so that it's pointing to the right. So that has to be R2 minus R1. And so if I add these guys together or subtract them, I'm going to get +4, 0 meters, which then gives me +4 meters in the I direction, which is exactly what we expected. So now we need the magnitude and the direction. So the magnitude and direction are the magnitude of R21 is equal to -4 squared plus 0 squared square root, and I'm going to get, of course, 4 meters. If I look at the direction, I'm going to have the tangent inverse of 0 and -4, which is, of course, 0 degrees. So in other words, I have my vector R21. It has a magnitude of 4 meters, and it has a direction of 0 degrees, exactly as we expected it. Now, putting this all together, I could then say that the displacement vector determines everything about Coulomb's force. So Coulomb force acts along straight lines where the direction of r hat to 1 is equal to the direction of the force. And in this case, it's going to be in the positive I direction. So we know that immediately. So the magnitude of the force is then going to be, I'm going to have the magnitude of F21, which we'll write as F21, is then equal to K. Then it should be the magnitude of the charges divided by the displacement vector. So if I start to put these numbers in, so I have my K constant, which is 1 in this case, because we're dealing with the toy model. So then it's the magnitude of the charges divided by their separation squared. So cancellation shows that this Coulomb cancels out with that. This meter squares cancels out with that. So I'm left with a unit of 1.20 newtons. So in other words, in vector form, F21 is equal to positive 1.20 newtons in the I direction. Now let's look at displacement vector 3,1. So what we said before is that we need a vector that's in the third quadrant. Okay, so we need that vector to be in the third quadrant. So now let's think about the displacements. So the displacements is, nope, the displacement is a combination of R1, which is -2 and 0 meters, R3, which has to be 0.3 meters. So if I combine these, I need to make sure it's in the third quadrant, then that displacement vector has to be a combination of R1 minus R3. So if I look at this thing, then I'm going to get minus, and I'm going to have 2I plus 3J in units of meters. That is a vector in the third quadrant. So doing this, I could then calculate the magnitude. So the magnitude and direction are as follows. I'm going to get that R31 will then be, I got to square these, so that is going to be -2 squared plus -3 squared square root, and that's going to give me a value of 3.61 meters. The direction is going to be the tan inverse of -3 minus 2. So remember, this is in the third quadrant, so we got to be careful with this. So I'm going to say this is -50. Let me be careful. I'm going to say 56.3 north of west. That's guaranteed that's in the third quadrant. So once again, if I look at my vector, I can rewrite this as 3.61 meters, and then I'm going to be at 56.3 northwest. There's my vector. So now that I can do that, now that I have that, now let's get the magnitude and direction of the vector, the force vector 3,1. So the magnitude is then going to be, it's going to be K times the quantity Q1, Q3 absolute R31 squared. So if I look at this, I'm then going to have 1 Newton meter squared per Coulomb squared times the charges of 4 coulombs, 5 coulombs, and then the distance of 3.61 meters squared. Again, looking at units, they all cancel out. And we see that we have a force of 1.54 newtons. But we need the direction, and the direction tells us that the direction of 3,1, which will then be the direction of force 3,1, is then going to be 56.3 degrees northwest. But this is a vector that has components. So we need to calculate the individual components. So the vector components of F31 are, I have F31x. Now by hand, I'm going to put in minus because that's in the third quadrant. I'm going to have 3,1 cosine of 56.3, and I'm going to get a value of minus 0.855 newtons. And if I repeat this process for the y component, I'm going to get minus by hand of sine of 56.3, which then gives me minus 1.28 newtons. So now I have my components, where in vector form, I see that I have that F31 now has F3ix plus F31yj. So this will be minus 0.855 newtons plus 1.28 j newtons. So this is my vector force F31. So now I can apply superposition. So let's look at this here. So graphically, what do we see? So graphically, the net force on Q1 due to Q2 and Q3 are something like this. So I have this guy right here. And so what do I see? Well, I know that F21 has a combination of positive 1.20 newtons in the I direction. So let's look at that. So I'm going to treat this as 1 Newton squares here. So then this guy's going to come out to about right here. So this is F21. Now, if I look at this other square here, what am I seeing here? I have a vector force 3,1 that reads minus 0.86 newtons in the I direction and 1.28 newtons in the J direction. So when I'm looking at this thing, I'm seeing that this guy has a component that's not exactly 1. This guy has to go longer than a square. Let's say it goes to here. So then if I do the superposition of these, I see that I have a force right here, and that's going to be force 3, 1. So if I do the parallelogram rule here, the parallelogram rule then says that I have to look at something like this, and you could see here is that now this is the net force right there. So that looks like that goes right into the fourth quadrant. So mathematically calculating, F net, we get that F net acting on 1 is going to be a combination of F21 plus F31. So if I start to add these quantities up, I'm going to get plus 1.20 in the I minus 0.866 in the I direction, minus 1.28 in the J direction with units of newtons. So then I have a quantity that then reads 0.34 in the I minus 1.28 in the J direction, and that points into the fourth quadrant as expected. So now we could calculate the magnitude and the direction. So if I look at this thing, the magnitude and direction of F net are, the magnitude says that F net has to equal F net x squared plus F net y squared square root, and that has to equal 0.34 squared plus 1.28 squared square root, and this gives me a magnitude of 1.32 newtons. And now if I look at my angle theta of the net force, that has to be the tan inverse of F net y, F net x, which then gives me a value of tan inverse of minus 1.28 divided by 0.34, which then gives me a value of minus 75.1 degrees. In other words, my net force has a value of 1.32 newtons in the direction minus 75.1 degrees from the x-axis. Now, to check this setup comes from Duffy's Coulomb law applet. So let's compare the results. So the first thing that we should look at is that let's look at the calculated one. And then we want to look at the applet one. So if I come over here and I paste in this is what we calculated. We calculated that we're going to have a vector that's going to be about, let's say, this length right here. And this is the magnitude of the net force. So this length here, we saw was 1.32 newtons. And it had a direction of 75.1 degrees below the axis. Now, if we go in and if I do a different share, and I go to the Duffy app, you can see here that if I focus on charge 1, that you could see that I have this combination, which is exactly what we already showed. But now if I change my image here just a bit, you'll see that this is what the Duffy app actually shows right here. And you could see that it matches up very well to what we actually calculated.